It's a pleasure to introduce George Pappas. He's a professor and the department head of electrical and systems engineering at the University of Pennsylvania. George has been working for many years in robotics, control, autonomy, verification, and is one of the leaders in this area for sure. He's won many awards for his work and had recognitions. I think the one in his bio that hit me the most was he has over 30 people from his group in academia, nationally and internationally. So, George, we're looking forward to the talk.
Well, thank you, Claire, Geir, and Institute for the invitation. So I'll talk a little bit about safe autonomy with trying to put deep learning in a feedback loop and try to analyze some elements of the overall behavior. So the vision, what I mean by autonomy are the kind of things that you see in the press these days, but I do think that compared to autonomy or autonomous systems that we have seen in the past, one main difference is that we are really sending them out in the wild compared to industrial robots or manufacturing lines of the 80s or earlier. And I do think that that makes the issue of perceiving and understanding the environment a much more important element, which then affects the control decision-making going forward. Of course, we've heard a lot about driving cars, and there's a lot of development in this area. But I do want to sort of say that recently, a few months ago, the Spectrum had an article where 5 years ago, we were promised, to buy autonomous cars. And I think now there's an understanding that while a lot of progress has been made, I think Peter brought this up, and maybe we are, 95 or 99% there. There's a lot of corner cases, which makes it still an unsafe proposition. And that is essentially why we have a lot of work to do ahead of us, and it's going to take a lot longer to get there. So when it comes, I'd like to start, I guess, the more technical part of the talk to say that there are two architectures that we have known over the past decade or more. I mean, if you come from a planning, robotics, control background, we have this kind of architecture that was, remained the main architecture for building autonomous systems. This is things that we have seen, for example, going back to the DARPA grand challenges and urban challenges. And, this sort of uses the concepts of modularity, abstraction, and perhaps at the very top, we'll see the core language that Cyan just talked about in the future. There's also a different kind of an architecture for autonomy that's emerging, and Daniela brought this up yesterday, which is, maybe we should let go of modularity and hierarchy, and then maybe connect, sensors to actuators, and maybe try to learn all of this in some composable learning framework. So I think what is the right architecture for autonomy is something that will, of course, be guided by many considerations. I'd like to propose at least our architecture or our approach, which perhaps is not so unconventional, and that is that we do need to have deep learning to coexist with planning and control. Deep learning has had tremendous successes and has become synonymous to the state of the art in computer vision and trying to understand the environment. So there's no question that when it comes to interacting with the outside environment, deep learning, for computer vision, at the very least, potentially for control as well, will have a very dominant role to play. Where there's been, of course, a lot of advances in planning and control over the last, few decades. And then, of course, the thing that's I believe, will bring the two together, essentially, especially in the context of autonomous systems, is what we know in robotics as mapping. And I think you can think of this as, deep learning giving us, representations of the environment, classifications, and things like that. But then we need to integrate those over time and create more integrated sort of representations of the environment that are more reliable, more stable, and then those are then being fed to control, planning and control, who has really used primarily more sanitized environments in sort of, getting guarantees. But now we're going to have to deal with different levels of uncertainty. And to some extent, this is the point I'd like to say that when we bring deep learning in a sort of a feedback loop, there's a new novel forms of uncertainty, and therefore we need to be thinking about new ways of mitigating this uncertainty by thinking about how to make deep learning perhaps more robust by itself, but deep learning will never be perfect. And to some extent, the mapping layer needs to be integrating all these uncertain measurements that come as an output from the deep learning, creating semantic representations of the environment, which I'll talk a little bit about, and then giving those semantic representations to a planning and control layer who will be trying to do its best to do safe planning or meet other mission requirements in such an unsafe or learned world. So I think the point here is let's embrace the deep learning. Speaking from at least to my control community, and let's see what deep learning has to say about control in such a feedback loop for robotics as well. But also perhaps there's something to be said in the other way. So the structure of my talk is to talk about three things. First, I'll talk about looking at each of these boxes as a sort of my technical outline. So I'll talk a little bit about our work on how to make this box here more robust. And then I'll talk about the other two boxes later. This is primarily the work of Maher Fazliab, but also Jacob Seidman, Alex Roby, and collaborators at Penn. And when we look at deep learning, of course, when you look at deep learning outside safety critical applications, and Sate made this point, then there's a lot of tremendous successes, Envision as well. But recently, the last 5 years, we know that deep networks are rather fragile, whether it is to adversarial attacks, if you have a security mindset, or it doesn't have to be adversarial noise or adversarial attacks. It could be that nature fools the deep network by changing, say, the lighting of an image, or changing the contrast of your sensor. And this, fragility or sensitivity of learning, sort of a problematic sensor in the context of safety critical systems. So certainly as a community, we need to be thinking about how to make deep learning more robust in order to apply it in this context. So you can certainly think of the fragility of deep networks as a sensitivity problem. So you have an image that could be the input to a deep network, and it goes through, and you get some kind of a classification to a symbol, like this is interpreted as a stop sign. But then, of course, if you add a little bit of noise and you pass it through a neural network, you get a very different classification. So, very similar inputs lead to very different outputs. And, we should be thinking about this as a sensitivity problem. So now, what are the paradigms for dealing with this sensitivity? Of course, in machine learning, there is a very large paradigm these days about how to make deep learning more robust using so-called adversarial training, where you, take a worst, more like a game theoretic view, whether you assume the data is perturbed by a little bit, and then you try to classify around the worst case perturbation of the data. This is something I'm not going to talk about, but I'm very interested in. Then in the more formal methods community, and in the, recently in the hybrid systems and cyber physical systems community, there is the paradigm that sort of assumes that somebody has pre-trained the deep network. So somebody essentially gives this to you as a function, f. And then you add some perturbation to your input, you push it through, and then you want to see what happens at the output level and whether you stay within a safe envelope once you evaluate your perturbed data through. So I'll talk more about this today. I'm happy to talk about this as well later, but I'll talk a little bit more about this. So if you look at the sort of the post-training verification of deep neural networks, how do we analyze input-output properties, say, of neural networks after training? There again, if you look at the formal methods community, there has been a paradigm which essentially, when you have rectilinear functions for activation functions, you can sort of map this into a mixed integer linear program, or if you come from a different group, you could be mapping this into a satisfiability modulo theory program. And that is an exact representation of the neural network, and you will get exact results, but you will not scale very well, even though there's a lot of progress recently. And the other approach is to sort of not go for exact results, to sort of pay a little bit of a price, using perhaps some linear and or convex relaxation of a problem, and then hopefully scale more. But you'll be paying a price at the error of your verification. So sort of, I'm going to talk a little bit about our approach, which falls into the second category. And our approach goes back to a deep connection between, that was known 30, 40 years ago, between actually backpropagation and optimal control. The two communities were talking a lot more at the time. They should be talking more in the future, and I'm happy they're talking a lot more. And you can certainly interpret a feed-forward neural network like this as a control system with a nonlinear feedback. So you can take, for example, your input, your data point here. It goes first through a linear layer, then goes through a nonlinear activation. Then you come back and there's another linear layer. So you go through a different linear layer. Therefore, this is a time varying system where the notion of time here is the number of layers in the neural network. And then you go again through the same nonlinearity, assuming all of these nonlinearities are the same. And then you go back, and then eventually the output system comes, you get an evaluation at the output. So analyzing then the sensitivity or the input output or other properties of this neural network could be, in principle, done by analyzing sensitivity of this linear time varying system with nonlinear feedback, where the nonlinearity is the same as the activation nonlinearity. And then, the hope here is that by analyzing sensitivity of these control systems, we can potentially say something about the sensitivity of the neural network. Okay, so you can view that as you go through the layers here, you can view this as trajectories of this system, and you'd like to see the sensitivity of the system when you add one initial condition, the stop sign, and another initial condition, which is the stop sign, plus some adversarial noise or some other perturbation around your data. So now the question then becomes, what can we really say about this class of systems, and how do control people analyze this, and how can they do it at a level that scales to some level that is useful for deep networks? So how do control people analyze? This is one approach, and this is our approach to hopefully scale to reasonable size. So we take we like linearity. Linearity is okay. And time varying linearity is also okay. The thing that is difficult to scale and have a computational approach is really the nonlinear activation function. So what we do is we take the input-output response of this nonlinearity, and we over-approximate it with a quadratic constraint. Okay, so the input-output, meaning that the input-output relationship between this input and this output through whatever the nonlinearity you've chosen, and there's a zoo of such nonlinearities, is strictly contained by this relation that relates the input and the output here. Okay, so this is an over-approximation of this nonlinearity. You do this for the whole network. And then essentially you have replaced the neural network, which can be interpreted this way, by something that is a linear system, time varying, with some kind of a feedback that is quadratically constrained. Okay, and therefore you pay a price. This is an idea that goes back to the 70s, this idea of analyzing systems with nonlinearity. And rather than computing, for example, the reachable set of a neural network, or say a sensitivity functions, we'll be paying a price. So we'll be computing something coarser, hopefully not too coarse, but this will allow us to scale perhaps more than other approaches. So this is what we did, and this essentially then is the key idea of this work, which is we take a neural network, we take we don't touch the linear activation functions, actually the linear layers, we just take the nonlinear activation functions and we replace them by quadratic constraints that over-approximate the input-output relation of the nonlinear activation functions. And you can do this, you can get different activation functions for different input-output activation functions here, one for ReLU, one for TANH, max, whatever, anything you want. So then rather than analyzing this deep network after training, what you do is you have some kind of a semi-definite program that tells you something about the input-output relation here. Okay, another way of saying it is that the input-output relation of this deep network is strictly contained into the input-output relation of this overall quadratically constrained linear network. And you can analyze a variety of properties such as robustness, computing the Lipschitz constant of the neural network, detection confidence, and things like that. So for example, we can compute the Lipschitz constant this way of a deep neural network. The Lipschitz constant is useful in a variety of ways. First, if you take a data point and you perturb it by a little bit, you can push it through, and the Lipschitz constant can very quickly give you what's going to happen at the output. But of course, the Lipschitz constant is also used as a regularizer. It's also very important for generalization bounds in learning and so on. The key thing here is, of course, the lower the Lipschitz constant, the more robust the neural network will be after training. Okay, so we can then take our approach and measure the sensitivity, let's say, of two deep neural nets. Okay, so again, our approach is conservative. So that means that since we cannot exactly compute the Lipschitz constant of this neural network, and this, of course, pictorially has one layer, but it can have many, but it will compute an upper bound to the Lipschitz constant. Okay, so we'll get some semi-definite program then that computes the upper bound to the true Lipschitz constant of this neural network. Okay, that's essentially the style of work here. You can also do other kind of analysis. You can take, for example, the distribution. You can pass through a distribution and you can, let's say it's a Gaussian or something like that, and you want to compute confidence intervals. So if you add some, noise to the image and this interval, you want to push it through, you can still use a semi-definite programming approach to compute not the confidence interval exactly, but sort of a lower bound on the probability that what you see, for example, is a stop. Okay, so the conservativeness here goes the other way. You compute actually a lower bound. This is actually something I'll need in the second part of my talk. Okay, so the other thing you could also do here is if you don't use the neural network necessarily as just a vision sensor, but also as a controller, maybe this is an image to action kind of controller, then what you can do is that if this is a linear system plus a quadratic constraints, and let's say this is your control system, but a linear system, then you can start analyzing the feedback interconnection of the overall system of how to get safety of a control system with really a deep network or controller. Okay, and there's a series of papers that address this, and we have also some tools that can do this. Let me skip this a little bit because in the interest of time, but I'm also interested very much in adversarial training for out-of-distribution robustness, but I'll skip that for now. So this is a little bit a high-level overview of our work here. Now, what I really want to talk about is when we take the output of such a vision sensor, how do we build semantic representations of the environment? And I'll be faster going forward. This is the work of Nikolai Atanasov, who's now at UCSD, Sean Bowman, and also in collaboration with my colleagues in the GRASP lab, Kostas Danielidis and his group. So if you look now in the world of robotics and you see what has been one of the greatest successes is that, SLAM is now a technology, and this allows us to make maps that tell us exactly where things are with reasonable precision, but the maps that we get are geometric, meaning that we know whether there's an obstacle or whether it's not, and this allows us to think about collision-free paths and things like that. But because of deep learning now and the successes in classification and object recognition, segmentation, and other things, we can now start thinking about new kind of maps that are not just about the geometry of the environment, but also about the semantics of the environment, not just about if it's free, the space is free or not, but also what objects are there, how they are related, and then use that to reason around those objects. And this is what we have done with our work in Semantic SLAM. You can think of this as, regular SLAM, if you like. But so these would be the regular SLAM inputs here. But now we take the output of the deep neural network as an input to our Semantic SLAM. So in particular, we'll be getting things like, well, at this location, I saw something that is, it's most likely a stop sign, and, probability that it's a stop sign is greater than 0.9. So I get this kind of semantic observations from the deep network, and, they go through the semantic SLAM, and what I get at the output is a semantic SLAM, a semantic map, as well as states. And what does that look like? And I'll best to describe it using a video. So here is what the deep network actually sees, and here's the classification that does. And then here, the output of this approach is creating this map, which integrates all this semantic information and builds semantic representations of the environment. So here we know, that there's this object here at this location, and there's a class of objects we can sort of enrich our environment with semantically. And then the green line is essentially the localization, what we call the sensor state here, which tells us where we are with respect to these objects. There's no GPS, no other localization. So we're just using, if you like, the vision-based localization here. So given that, now we can start reasoning a little bit about objects in the environment, which is something that's important. But I would like to bring up also a point that I think Rujuna brought up yesterday, which is it took us about a year to get the Semantic SLAM machinery to work at a rate of 5 Hertz. So getting this to work at real time is very important if we're going to put these things on a robot. You can train offline, but then you have to do all these computations in real time so that this can be on a robot. And I think that it took a while to get there, and we're happy that this is offline. This is not on the robot. I'll show a robot later, where this is what the Semantic SLAM does in action with the so-called Kitty dataset, which is a standard dataset for this. So you drive around the city of Karlsruhe, you have a detector that looks at cars and windows, and you are making a semantic map of the city, which is sort of you're mapping all the cars in a city, and then you're also localized using those semantic observations to localize yourself in the city without any GPS, in a GPS-denied environment. Okay, and if you go later, you'll start seeing a much larger semantic map of the city. So you can imagine driving around and enriching Google Maps with all kinds of semantic objects, and maybe in the future, one can also do richer types of relationships between objects. But right now, we just do types and poses. So that's a high-level overview of how we aggregate the output from the deep learning to do semantic mapping. And now the planning and control layer has to take the semantic representation, take some requirements, specification, safety, and then generate either plans if you're at a higher level or controls at a slightly lower level to the robot and execute. And I think here, the change I think that needs to happen from a planning and control perspective is that I think a lot of planning formulations assume rather very sanitized or known or environments with a lot of structured uncertainty. And I think here we're in a situation where we don't know much. We go out and we learn the environments, and as we build representations of the environment, we have to react and plan with some level of confidence. And I think so the question then is, how do we incorporate the kind of representations that's deep learning gives us, and perhaps through something like our semantic map or other representations, and then how to reason about those in our planning, at least in this context. The other thing is, how do we, and I think Hadas brought this up yesterday, which is how do we think and reason about safety? And I'll have one answer, but I'm not, there may be many, many more to think about here. So the representation at the end of the day, what we get is, if you're in the geometric SLAM space, you can think of something like an occupancy grid map, which is basically telling you which part of the environment is free or not, and then you can reason about paths there. But when you deal with our semantic map representations, then what you get is a map that looks like this. There's something here. Most likely it's a chair, but it could be a door or it could be a table. Okay, and also I'm not so sure where it is. Maybe there's some ghost. So there's uncertainty both about what it is semantically and where it is from a location point of view. And now we have to choose and to make plans and paths in this in a safe way. And as the map changes, we have to improve, adapt, and/or we may choose to move in order to reduce the uncertainty of the map, which is also something to consider. So effectively, going back to our architecture, all of this is now abstracted from the control point of view as some kind of an uncertain map, which could be dynamic, static, and we can talk about those variations later. And we are given a semantic map, which has some uncertainty representation. I think the important thing here is that we need some level of uncertainty around these maps. They're not just, certainty equivalence doesn't work anymore here. We have to really reason about the uncertainty of the estimate in here. And we have the safety specification, which could be as simple as, go from point A to point B while avoiding obstacles, or something more elaborate in the specification mechanisms that we've seen already. We may have also dynamics, high level or low level. And the thing is, the question is how to generate either sequence of controllers, acceleration profiles, whatever you want in order to meet. And I guess here the point is that, and I think JP brought this up yesterday, which is, I really believe that in this case, we're going to have to deal with some notion of probabilistic correctness, which is maximize the probability of satisfying the specification in a given map. And if you have dynamics in the map, then in the evolution of the map. And I leave this a little bit informal. There's a formal way of writing all of this as well. Now, this is a very hard stochastic optimal control problem, or problem with a lot of uncertainty. The way we have approached this is by using sampling-based approaches, which sampling-based approaches have been very important and successful in robotics. But here we're not just sampling the physical space of the robot about where to go. We also have to sample the information spaces. So maybe by moving somewhere, we may reduce uncertainty. And you can think of this as an exploration, exploitation kind of a trade-off, which makes then the sampling, the biasing approaches very important, which way, how to tune that, which is something to discuss as well. And then if you have a more elaborate specification, then you have to treat about, you may want to sample the specification space as well. Which part of the temporal logic formula, for example, have I achieved, and maybe which one I can move next. You can show what you typically would want from a sampling-based approach, which is that there's some probabilistic completeness of the algorithm if you have a lot of time, and that you can have some notion of asymptotic optimality. So this allows you then to have really autonomy, even or collaborative autonomy in this context, in a totally unknown space. Where there's both metric uncertainty, in this case, we don't know anything about the building, as well as semantic uncertainty. We're supposed to meet, satisfy this temporal logic spec, but we don't know anything about all these actors. This is a little bit like what science sort of mission was, where they have to go and deliver supplies at all these things, but there's also an adversarial actor here. And we don't know who is who. So there's semantic uncertainty. Maybe 2 and 4 are flipped because we don't know who is who, as well as we don't know where they are. And then when they complete the mission, they are supposed to get out of the building, but they don't know where the exit is. In this particular case, they share a map. You can imagine future versions where you also distribute the map as well. And then eventually they get out. This is a ROS version of the previous experiment. This was around the time before COVID. So this is part of, so here we have a gazebo kind of simulation where we know the geometry, but we don't know, there's some targets, and we're supposed to go out and find them, track them, localize them. So there are 16 landmarks and 20 robots. Okay, there's no deep learning here, but in the next one there will be. So this gives you a little bit of the three pieces. In each of these pieces, there is code that you can download from GitHub or other places. And each of these tell you a little bit about how to reason or improve the robustness of each of these components. We would love to have a way to reason about the integrated system. We, of course, in the case of deep learning as a controller with a linear system or even a piecewise affine system, we have such guarantees. But in the more general case, I think having some kind of a calculus for reasoning, like the verification engines that, or the proof calculi that Cyan mentioned, that would be wonderful. But we can certainly see how it works in practice when we empirically put everything together on a robot. And this is what we have done. And this is collaboration with Dan Kodicek's group, as well as Kostas Daniilidis' group at GRASP, where we have, as you can see, the deep network, which is the key point detection. This goes to the semantic mapping, which then goes to our planning layer. And then we also have a second neural network that does human mesh estimation from Kostas's group. And here we're trying to track a human in a totally unknown space. Okay, and this goes on the robot. And here is experimental results that show you how this works in action. So here you'll be seeing, here's the, ghost robotics kind of robot. Here you can see what the deep network sees. And here is the semantic map that we build using semantic SLAM. And then, that's fed to the reactive planner then that actually decides. And the goal here is to track this human in an unknown environment where we of the objects, here. So these are being detected by deep learning. We create the semantic representation of the space, and we're trying to track this human right there. And then, because the architecture is robust, we can switch environments and go somewhere else. And it seems to work rather robustly. No changes, no retraining, nothing. So that's the advantage of, I think, of trying to be, to aim for more robustness in each of the components. So again, same task, try to track this human, different corridor, different ground, actually. And things work rather well. And I can accelerate this, and you can see sort of the semantic representations here that you make. And then we take the same architecture, and then we do indeed go outside in the wild. Okay, so this is going a little bit further out. So last experiment before I end my talk, and then we go really outside our new robotics building here, where again, different lighting conditions and all these things, and you can sort of, very robustly sort of execute the same task, in an unknown environment. And okay, so I think empirically, at least, we were able to show that this works rather well, and we feel very confident when we do experiments now that things will actually work the first or the second time we do everything. So with that, I'd like to conclude my talk. There are many interesting things for the future. I think here we're really excited about using some form of, thinking not so much about adversarial attacks where we have adversarial, perturbations to the data, but rather more perturbations that we see in practice, such as lighting changes. So this is one direction we're going. Scaling convex optimization to the kind of neural networks that we see in deep learning is, of course, a big challenge, an interesting challenge from the convex optimization also point of view. Now we can go to deep networks that are in the, let's say 50,000 nodes or activation functions, so that might be okay for like deep reinforcement learning, but not okay for, the convolutional neural networks we see coming out of computer vision community. I think on the SLAM side, I think one of the challenges going forward is, enriching the representations with different features, but also thinking about dynamic environments. And then on the planning and control side, I think how to go more distributed and how to even reason about uncertainty, whether it's in the planning or in the specification, is something that we're thinking about. So with that, I know I'm a little bit over time, but I'll stop here. Thank you.
Okay, thank you, George, for a very exciting and comprehensive talk. We've almost used our buffer, but break buffer, but I think we have time for one, relatively quick question. Is there a question out there?
Pete Seiler asks a question in the chat, or I see Jeff there too. So maybe Pete and Jeff.
Yeah.
Pete, why don't you
so
speak up?
I read the question. Yeah. So it's a great question. Indeed, different activation functions lead to different quadratic over approximations. And we did do some experiments where we wanted to see which activation functions are, you're bringing the right point, which are more conservative or less conservative. That's one thing. But also from a robustness mindset, which was our original mindset, we wanted to see which activation functions make the neural networks less sensitive to the input. So we did exactly what you're saying, but not from the perspective of accuracy, even though that is a very important question. But we looked at it more from which activation function reduced the Lipschitz constant, let's say, of a neural network. But it is an excellent question, and hopefully there's more work to be done by many of us.
Okay, let's take a 4-minute break. There are many questions that from this talk, I think, that we'll follow up in the panel. So thank you again, George, and we will resume with Katie Driggs-Campbell at 1/2 past the hour. So about 3 minutes now.